projectile motion. So projectile motion here. So what's a projectile? Well, a projectile is a thrown or launched object that is only influenced by the force of gravity. Okay? So thrown or launched object, or even a dropped object actually. Only under the influence of gravity. Now I'm going to put a little star by that, because that's kind of the description of an ideal projectile, where we can neglect things like air resistance or friction with the air, or the compressive reactive force of air as an object moves through it. Okay, so this is an idealized projectile. Okay, so idealized. And an idealized projectile and a real projectile act a little bit differently. So we're going to start with idealized ones, and then we're just going to briefly discuss what happens if you actually do talk about air resistance. So we're going to start off here with just putting that on the table. For these problems, neglect air resistance. All right, so the first kind, and we've sort of covered this a little bit with within kinematics, is just dropping a ball. Okay, so let's say we take a ball up high and we drop it down. Okay, that's a projectile. Or we could take a ball and we could throw it up. And we will find it goes up and then comes back down. Okay. Now, as this ball falls, what we'll notice is that its speed increases. Okay, so it gets faster and faster. This ball will first slow down as it reaches the higher height, stop, and then follow essentially the exact opposite scenario on the way back down. So there is an acceleration due to gravity in these objects. Okay. All right, and there's also this type of projectile. Now, this is where it gets a little more interesting. Say we have a cliff, and you take a ball, and you send the ball flailing off the side here. Okay, you would say that this ball has an initial velocity, but you would also define what direction that velocity is in, and we'll talk about why that is. So we're going to say this is u in the x direction. So initial velocity in the x direction is some value. We're also going to talk about the other component of this and what it is doing in the y. And at first, it's doing nothing in the y, right? If it comes, flinging straight off of here, it's doing nothing in the y. So what it's going to do is going to follow this sort of half a parabola down towards the ground. We just want to examine why it is that it follows that particular type of a path, okay? And here's the reason. If we look at the ball as it travels along, as time goes by, okay, its velocity changes, right? Its total velocity at the beginning, it's just straight horizontal. But then its velocity comes to here, and then to here, and then by the time it hits the ground, its velocity is more like that, right? And here's the reason why. Okay, so remember we're neglecting air resistance, so therefore in the x plane of this, right? So we've got our x and y plane. In the x plane, there's no acceleration. But in the y plane, we do have acceleration. We have gravity working on the object, so pulling down in the downward plane, just like it would on a ball launched straight up. Okay. So as time goes by, this ux stays the same. Okay. I highlight it all. I don't know if I can. Sort of can. Okay, and I actually want this thing. Oh no, it has that in it here. Okay, so the velocity in the x direction, right, just does not change. But the velocity in the y direction does, right? It grows. So right here, you've got that. there's your net velocity there, right? So we call this, it's not u anymore, right? So this is now vy, the velocity in y, and it gets larger and larger as time goes by. And the resultant is the path that your ball is taking at any given moment, okay? So the combination of no acceleration in the x, but an increasing velocity in the y, works out that your ball is going to follow this parabolic path towards the ground. Does that make sense? The other interesting thing is it does not matter how fast you launch it in the x direction. All objects from this height that start with an initial velocity in the y of 0 will all hit the ground at the same time. So that also means that if I drop the ball at the exact same time as this, I'm going to see that it hits the ground at the same exact time that the parabolic path object hits the ground at. And this was done by experiment by Galileo way back when. And how he explained that with a thought experiment, how this could be true, because oftentimes people believe that the dropped object would hit the ground sooner because this has to follow a farther path, is the famous ship experiment. So what he said was, imagine if you got a ship sailing on the ocean and someone is up in the crow's nest and they drop a ball. Okay? So from their perspective, that ball is going to fall down and it's going to land straight below them on the deck of the ship, right? But if in the meantime that ship has sailed along over to here, okay, well, someone on the shore is going to see a different path, aren't they? So here's someone standing on the shore, you know, watching this ship sail by, okay, and they're going to see the ball do this path. Okay, so they're going to see that famous kind of curved, I didn't draw it very well, but curved parabola. Is this different motion? No. The time that it takes to get from here to here is the same, regardless of how you view this scenario. Okay? And if you want to continue this to its logical conclusion, you could also think about it like this. Imagine this instead. Let's say I just drop a ball straight down from a tabletop here. Okay, so here's me, got a ball, and I drop it, right? Say I'm up on a ladder or a ledge or something, okay? And it falls straight down. Well, from my perspective, it falls straight down. But imagine that somebody is like getting rolled along in like a little cart or something. They're sitting on a little cart that's rolling along, okay? And they're watching this scenario. Well, what are they going to see this ball do? It's going to end up further behind them each time, right? So they're going to kind of see it, you know, if you imagine that their perspective is still, what they're going to see is this is the same as if this were moving away from them in that direction. And they're going to see the path of the ball fall, a parabolic curve just like this. And of course, what they would notice is that this person has, from their perspective, moved over here, right? So what we're saying here is that how you observe something, your frame of reference, is very important in how you're going to observe these things. And we say that time, regardless of your frame of reference, at least for things moving, you know, relatively slow, is the same. So this takes the same time as this. This takes the same time as this. So it's all about how you're observing these objects happen. Okay? So if someone tells you that if you shoot a gun from a high, you know, place straight horizontally and you drop an identical bullet, both those will hit the ground at the same time, well, that person's telling you the truth, right? As long as there's no like aerodynamic effects, as long as the air isn't you know, causing lift on the bullet, like if it's spinning or rifled or something like that, okay? So it makes sense logically that a dropped object and an object launched horizontally with no vertical component to velocity at the beginning will hit the ground at the same time, okay? So projectiles, these are them, and there's one more type of projectile we'll look at, and then we'll crunch out the math on all of this. So the last one, we'll use an example of a kicked football flying like this, okay? Okay, so this football is going to follow a parabolic path Of course, this is only true if we neglect air resistance, which we would, okay? And what's important here are a couple of things. So here you're going to have your initial velocity, let's call it the naught value, u naught, and this will have two components. It's going to have uy, an initial velocity in the y direction, and ux, an initial velocity in the x direction, okay? So this is, actually that's slightly confusing because it should be up, right? So uy is an upward initial velocity, and ux is a horizontal or rightward initial velocity. And interestingly, uy will follow the same physics laws as any object thrown up with an initial velocity of whatever uy works out to be. All right? So what's going to be important here is the angle that it's kicked at, so theta, and the initial velocity that it's kicked at. I want your ball to go far, kick it really hard, and kick it at the proper angle. In that case, 45 degrees will get you the longest distance. Now, while we're on this topic, an idealized launched projectile will follow a perfect parabola. But in real life, there's air resistance. So objects do not follow perfect parabolas. What would happen here is as this object is slowed in both the x and y, you get a path that's much more like this, okay? In ancient times, people had a lot of trouble understanding the mechanics of how launched objects traveled. You go by Aristotle's view, for instance, he thought that objects traveled in straight lines or either horizontally or vertically. So you would have violent motion in this direction. The object would travel along a straight path until the force you had put into it wore out, and then it would transition to its natural motion, which would be down, right? If you remember what we talked about with Aristotle, he said objects went to their natural place. So if, the football is made of, earth and water, it would tend towards the center of the universe. So if you pick up a football and drop it, it goes back to the place where it belongs, right, the center of the universe. And if you want to move it in any other direction, it requires force. That's the way Aristotle looked at it. So people kind of, I guess, going by that mentality or that view, thought that this is how objects moved, right? And it wasn't until the time of Galileo that this was kind of corrected. Now, if you look at this, it's not actually really completely unreasonable that this is what an object apparently does, right? If you throw something light like a badminton birdie or something like that, this is essentially exactly what it's going to do. It took Galileo to see that if I could remove the air resistance, I can get a much better picture of how objects are really flying or moving through the air. This is a little bit of the historical context. So this is not right, but it's reasonable, I guess, considering the understanding that ancient people had of the way objects flew. Okay, so let's get to the math. So the first one we'll look at is dropping. So I take an object, drop it down from some height, okay? I am going to use my famous formula, S equals ut plus 1/2 g t squared. Okay, the acceleration of this formula is the acceleration due to gravity. The initial velocity for a dropped object is 0, so u times t will cross out. Okay, if I want to figure out the time it's going to take to get to the ground, the distance is actually the height, so we'll just rewrite it as h equals 1/2 g t squared. And what we would be interested in here is finding a value for t. So we're going to get 2h over g, and we want the root of that. So that is the time it takes for any object to fall from height h if you neglect air resistance, okay? And if it's on Earth, this value is 9.81. If it's on another planet, it's whatever the g value is on the other planet. Does that make sense? We've dealt with problems like that before. It's not really a huge deal. Now, the other thing you might want to know is what velocity does it have at the end? So what is its v? Okay, so we also have this to deal with that. V squared equals u squared plus 2a Well, it's S, but we're talking about height here, so 2AH, and A is actually G, so we get that. We said when a drop object falls, U is 0, so we simply get V is equal to the root of 2GH. Is there another way we can arrive at this? How else can we get there? Sure. If we have gravitational potential up here, and that gets converted into kinetic energy down here, well, gravitational potential is found as mg times h. Remember, that's simply from here, right? There's your force, there's your distance, right? So force is mg, distance is height, so we're storing this energy. And ek, 1/2 mv squared. If we make them equal to each other, we get this. And mass, of course, does not matter. Again, counter to what Aristotle said, right? He thought that the bigger the mass, the faster it fell. So multiply the other side by 2. Okay, so 2gh should be equal to v squared, and then root it out. And you have kinematics and energy agreeing with each other. Of course, they have to. If they didn't, we'd have problems. Okay, so there it is. The, I guess, simple math of a dropped object. Okay, and maybe I'll just box this because this is important to know too. Okay. Next thing is a up throw. So, kind of similar. Essentially, you throw an object up, it comes back down. Well, the second half of this is identical to what we just did above. So if you want to find the time it takes to fall down, okay, just look above. Time is root 2h over g. Now, the problem here is we're not often given the height that the object goes to, are we? What we usually have to start with is simply this, the initial velocity in the upward direction. So u in the y direction. There's no x here, it's just thrown straight up, and it's coming straight back down. Okay? So what we're going to find then is the time to a velocity of 0 is going to be this. T is equal to delta v, so the change in velocity, right, divided by g. Well, this should be final minus initial, so v minus u in the y over g. And just continuing down here, t then should be equal to, well, if this is 0, right, its final velocity is 0 when it's at its max height, we get this, negative uy over g. Now, why is there a negative value on here? Right, because we're, in this case, saying g is down. So, depending on how you want to look at this, personally, I like to get rid of that because I realize that the signs on these two things are the same, right? The change in velocity is going to be in the same direction as the accelerating force on the object. Does that make sense? I mean, you can't have a force causing an acceleration opposite to itself, at least that I know of, okay? So I prefer to just leave off that negative because I find it can cause confusion. If you forget that there's a negative on here too, you're going to get a negative time, and that would not make sense. So it's up to you as the physicist to kind of realize how you're going to treat the negatives and positives here. Personally, I just yank it. It makes more sense to me that way. Now, what is this telling me? Well, this is the time to get to the top. How much time does it take to get back down to the bottom? The same. So in other words, if we want the total time, or we might call it hang time, we got to multiply this by 2. 2 times uy over g. That's the total time that a launched object at an initial velocity will be in the air for. Okay? Total hang time. Okay, next. 3. Cliff ranged projectile. What's the math there? See, most of this should be pretty much straight up review from kinematics, right? Okay, so ball gets launched, away it goes. Okay, now we define this down here as the range. The range of the projectile. Range. You could also, I guess, call it Sx if you want, distance in the x direction, and usually this is called height. The time that this object will be in the air is exactly the same time that any object dropped from this height, okay, will take to hit the ground. So we can say air time is simply what we found before. It's the root of 2h over g. Okay, that's how long it will be in the air. Now, how far it goes is based on this. If you know ux and you know the time it's going to be in the air for, it's just a simple classic distance formula, right? All you're going to say is this. The range is found as velocity times time, right? So ux times t. Or we could say in more mathematical terms, Sx is equal to ux, your initial velocity in the x direction, times time, but time is equal to this. So times root 2h, that's the height of this, divided by g. Okay? Do you have to do it in one single formula? Not at all. You can find this piecemeal. Find the time first, then do a range formula. Or we can compact it into a new formula. Just totally up to you, right? Are there any questions at this point? So far, so good? Making sense? Awesome. So this is range. How far an object rolled from the top of a cliff will go. And just going back to this, you might be asked, what is the velocity of this object at such and such a time before it hits the ground? You're going to have to do some vector addition in that case. Okay? You're going to have to know that ux does not change. There's no acceleration in the x-plane. And you're going to have to find what its velocity is after such and such a time. And you're going to have to do a vector addition here, right? There's your vy. The sum of those two is the actual velocity on the ball at that given moment. Okay? Interestingly, the velocity will always be the tangent to this smooth curve that goes along here, this parabolic curve. So it's the tangent to the parabolic curve. Okay, and last but not least, let's talk about the distance that a ranged or launched projectile will fly. Okay, so we'll say like this is like a cannonball or a baseball or something like that. And we're going to do the idealized parabolic trajectory. So no air resistance at play here. Oftentimes on a test, you might be asked to draw the parabolic path, but then to also go back to your drawing and show the actual path with air resistance. So we know it's going to kind of peel off of here and end up much shorter than its true value. Okay. Now what we need to know about this is the angle of launch, the initial velocity, or u0, and then you're going to have to find the components of u0. So you're going to need a uy and a ux, and they're going to act independently of one another. So again, like we talked about with the cliff-launched object above, if you can find the time this object is in the air, and you realize that it's chooching along in the x direction from the time it's in the air, you could figure out the range that this object will go. So you find the hang time in the air, and remember, if I launch this object, right, it's going to follow along this path, you know, like this. And if I were to throw a ball up at uy, what you would find is that ball thrown straight up is always going to end up at exactly the same height above the ground, the same vertical height as this object. These will like match up perfectly with each other, okay? So if you know a way to figure out how long the object will be in the air based on its initial y velocity, then it's actually not that hard to figure out how far it will go. And you just multiply that time by the velocity in the x. So we said from before, the time for any object launched up, okay, is going to be based on uy. So what we can say then is this. P total from before is now going to be equal to whatever uy is. Now remember, this will end up with a negative value on it, but we dealt with that before, times g. Now we're just going to say the signs are the same, so we're not going to put them in. Now, the question is, how do I find uy? Well, I find uy based on the angle of launch and u0. So this is the opposite angle. So uy should be found as u naught times the sine of theta over g. And one thing I forgot, we want the total time, right? This will just be time up to the top. So we got to drop a 2 in front of that. Okay? So the total time that my projectile is in the air, the total time from initial launch to hitting the ground, is 2 u naught sine theta all over g. Okay? And if we want to know the range, how far it goes, right? We simply have to take the total time and multiply it by ux. So range then is going to be equal to u in the x direction times the time total that we had from here. Okay? How do we get ux? Well, it's the adjacent angle to theta. So we just do this. Range equals u naught cos theta times time total. Okay? Now you can do this all piecemeal and figure it out. Or we can now punch in what we found for t total, and we can create ourselves a brand new formula for a range projectile. So let's do that. So I'm just going to change range to sx, so distance in the x, is equal to u naught cos theta times t total, which is 2 u naught sine theta all over g, right? So I've substituted this with what I have for t total. So I get this. Now let's just do a quick rearrangement here and pull some terms together. So we've got, this should be equal to u naught squared times 2 sine theta cos theta all over g. And math class time, who recognizes this as a trig identity? Well, I don't know why you're groaning. It's a simple trig identity. Well, perfect. Then the timing is just right. 2 sine theta cos theta is the same as saying, well, don't worry, I'll help you. It's the same as saying sine 2 theta. Okay? So this trig identity right here, this comes from math class. It's just saying 2 sine theta cos theta is equal to sine 2 times theta. And there you have a way to find the distance that a range projectile will go, okay? Based on its initial velocity, whatever its theta value is, and of course, g. So this is the distance that a range projectile will go, okay? And it's just a matter now of understanding when and where to use these things and doing a little practice with it, okay? And we're almost out of time, so I'm going to wrap it.